The Earth's so-called greenhouse effect is the ability of certain gases in our atmosphere to absorb the radiation emitted from the surface of the Earth, while letting in most of Sun's radiation. It's absolutely critical for life on Earth. Without the greenhouse effect, quite simply, we would all be dead, frozen to death on a frigid planet. With a stronger greenhouse effect, we would also all be dead in a boiling hot atmosphere. We humans live in a small window of survivability, in a tiny layer of gas strapped hard by gravity to a sphere of rock that is mostly deathly hot, aside from the near-surface rock and water that we wander about on. For the foreseeable future, we are trapped in this layer. It's our beautiful prison. Any vacations beyond up high mountains in aircraft or spacecraft are, for the moment, temporary. This video is designed to present an explanation of Earth's greenhouse effect that is understandable to anyone. So please, if you're confused by any aspect, leave a comment below so that I can improve future versions. The story of the greenhouse effect starts with the Sun, where thermonuclear fusion reactions in the interior convert hydrogen into helium and release huge amounts of heat energy. This energy is then shot outwards in all directions through the solar system and beyond in the form of electromagnetic radiation. A minuscule fraction of this energy arrives at Earth and is absorbed into the climate system, providing the energy input for the greenhouse effect and the driving force for storms and ocean currents. So first of all, we need to know a little bit about this electromagnetic radiation thing. Electromagnetic radiation comes in the form of waves of alternating electric and magnetic fields, traveling at the speed of light. Electromagnetic waves can come in a huge range of wavelengths. These waves can be larger than the size of buildings, all the way down to smaller than atoms. And this massive range is known as the electromagnetic spectrum. The bit that we can actually see with our eyes is known as visible light. It is only a small section of the spectrum that the human eye has evolved to detect and interpret in the brain and into our consciousness. Why do we need to know about this spectrum of radiation to understand the greenhouse effect? Well as the Sun, the Earth also emits radiation, but it does so at mostly longer wavelengths than the Sun, and it is this fact that is absolutely critical in enabling the greenhouse mechanism, because atmospheric gases respond very different ways to different wavelengths of radiation. Since the Sun provides the energy input for the greenhouse effect, an obvious first question is how much energy actually arrives from the Sun when it reaches Earth's atmosphere. At the surface of the Sun, the energy flux is about 63 million watts per meter squared. But as this radiation travels towards Earth, it spreads out and weakens, but the wavelengths of the radiation remain the same. After traveling 150 million kilometers in 8 minutes, the radiation reaches the top of Earth's atmosphere, and its power has dropped to an average over a year of about 1,362 watts per meter squared. That directly faces the Sun. This important value is known as the solar constant, although it is not a true constant, as it does vary by small amounts, with the yearly average varying about 0.2% over the last 400 years. What does watts per meter squared actually mean? Well, a unit of energy is a joule, and we want to know how much energy is being received over a particular area and over a particular time. A watt is the energy per second, so it's the joules per second, and it represents the rate at which energy is transferred. The per meter squared then determines the amount of energy being received per second in a square with 1 meter sides that lies directly facing the radiation, which in this case would be facing the Sun. However, the Earth rotates, so half of it is in the dark of night at any given time. On top of that, because the Earth is a sphere, most of the surface does not directly face the Sun. The energy hits a circular area perpendicular to the Sun, but over a day-night cycle, this energy is spread over the surface of a sphere. So to get an approximate value of the solar energy received at the top of Earth's atmosphere over a full day-to-night cycle, we just have to divide the area of a circle by the area of a sphere, and multiply that fraction by the solar constant. Pretty simple, as it turns out. We just have to divide by 4, and that gives us a value of 341 watts per meter squared. This is of course an average, as the actual value varies largely between the tropics and the poles. Now of this 341 watts per meter squared, a portion of this energy is immediately reflected, Some of it is reflected by Earth's surface, particularly bright surfaces like snow and ice. Another portion is reflected by clouds, and we can see this occurring by how they appear bright and white from space during the day. In all, roughly 30% of the 342 watts per meter squared is reflected, which leaves us with about 238 watts per meter squared of sun's radiation that is absorbed into the climate system. So on average, this essential quantity represents the input of energy pumped into the greenhouse process. But what about the wavelengths of this energy? To determine the wavelengths of this radiation that drives the greenhouse effect, there is another concept that we need to introduce, and it's the concept of black bodies. It's fairly simple and goes like this. All objects emit radiation, so long as their temperature is above absolute zero. That's 0 Kelvin or minus 273 degrees Celsius. That means that the ocean emits radiation, the air emits radiation, you and I and everything else on the sun and earth emits radiation. But materials at different temperatures emit the most radiation at different wavelengths. It's easy to understand and works like this. The hotter the object, the shorter the wavelengths emitted. Simple. But how can we find out what wavelengths are emitted by different objects at different temperatures, like the sun and the earth? To do this, we imagine an ideal material called a black body that perfectly absorbs and emits all radiation. It turns out that while the sun and the earth and many other objects in the universe are not perfect black bodies, they're not that far off. In fact, the radiation that they emit can be approximated quite well by looking at the black body radiation for the object's temperature. So first of all, let's take a look at what this means for the radiation coming from the sun. The radiation from the sun that arrives at Earth originates in the outer layer, which is known as the photosphere. The photosphere is obviously incredibly hot at between 4,500 and 6,000 Kelvin. That's between 4,230 and 5,730 degrees Celsius. And we can use its very high effective temperature to determine what wavelengths of radiation it emits. For our purposes of looking at the wavelengths of radiation emitted by the sun, it's best to consider an effective black body temperature of 5,778 Kelvin. At this temperature, the wavelengths of radiation expected to be emitted are shown on this chart, which is the wavelengths along the bottom on the x-axis, with the energy on the left, the y-axis. At the top you can see the ultraviolet, visible and infrared wavelengths labelled for reference. This black curve now shows the expected energy received at different wavelengths for a black body with the sun's surface temperature. Based on this, we would expect that the radiation from the sun to be most intense in the wavelengths of visible light, but it should also emit radiation across a range of longer and shorter wavelengths. But is this actually true? Well, nowadays it's easy to find out because we make measurements of the radiation arriving from the sun at the top of the atmosphere. So let's overlay these observations on the chart as the yellow area. Now it's clear that the expected radiation and the observed radiation are quite similar, with the observed radiation also peaking in the visible part of the spectrum. So now we know the wavelengths of radiation that the energy from the sun has as it arrives at the top of the atmosphere. But now that radiation has to pass through Earth's atmosphere to reach the surface. So how much of this energy actually reaches the surface? Well, the sun's radiation at the surface is also measured, so we can plot that on the graph as well. And this is shown as the red filled area. The red area is smaller than the yellow area, indicating that energy has been lost as the radiation passed down through the atmosphere. This is due to the interaction of radiation with the particles and gases in our atmosphere. So we'll begin part 2 of this video with a look at what exactly is in the atmosphere that interacts with the sun's radiation. And then we'll continue on to look at the hugely different interactions that occur as Earth's radiation attempts to return the energy back to space.